The Big Bang Theory proposes that the universe originated from nothingness, marking its beginning. Before this event, there was no time or space. However, what if I told you that time doesn't actually exist and the Big Bang Theory could be incorrect? That's the view held by renowned scientist and Nobel laureate Sir Roger Penrose. Penrose is among those who argue against the idea that the universe emerged from nothing. He suggests that there was neither a beginning of time nor of the universe itself. What's particularly intriguing is his belief that dark matter, often theorized to exist based on astronomical observations, is not actually present in the universe. Now you may wonder how the recent data supports the concept of time having no beginning, and why Roger Penrose disputes the existence of dark matter in the universe.
There is this dark matter, which seems to be out there, which dominates the material of the universe. It's by far the majority of the material substance in the universe. It's called dark matter. Nobody really knows what it is. It's the major part of the mass of a galaxy, and it's first observed because of the stars going around. They go around too fast in order to compensate for the extra attraction of this dark matter, and that's how it was first observed. And all sorts of observations, cosmological, tell you it's there. Now, if it's there, and if it's really gravity, because it's picked up on the gravitational degrees of freedom, there's nothing else in physics going on with regard to it. It tells you something about what it ought to be. Now, one thing it ought to be, and I think I've listed these things here if you can read them. One thing it ought to be, what's its mass? Well, the only thing it can be, if you've just got gravity, roughly speaking, is a thing called the Planck mass. Well, it might be 8 pi times it or something or other. But it's something of the order of the Planck mass. How big is the Planck mass? It's about 10 to the minus 5 grams. That's about the mass of the eye of a flea, I believe I got from Google or something. Now, that is huge if you're talking about particle physics.
In 1981, many of the world's leading cosmologists gathered at the Pontifical Academy of Sciences, located in a villa within the Vatican Gardens. In this setting, Stephen Hawking chose August to present what he later considered his most important idea, a proposal on how the universe could emerge from nothing. Before Hawking's presentation, both scientific and theological explanations of the universe's origins faced the same question: what happened before that? For example, the Big Bang Theory, introduced by a Belgian physicist and Catholic priest, Georges Lemaitre, traced the universe's expansion back to a hot, dense bundle of energy. Yet the question remains, where did this initial energy come from? The Big Bang Theory also faces other challenges. Physicists know that an expanding ball of energy would likely become a chaotic mess, rather than the smooth, vast universe observed by modern astronomers. Stephen Hawking, renowned for his intelligence, offered a unique solution to the quest to look back in time. He suggested that there's no beginning or end at all. During a Vatican conference, a 39-year-old physicist from Cambridge University, still able to speak, addressed the audience. He suggested that the universe's boundary conditions must be truly unique, proposing that the most unique condition could be that there is no boundary. This no-boundary proposal, fully detailed in a 1983 paper by Stephen Hawking and his collaborator, James Hartle, envisions the universe as a sphere. This sphere starts with a diameter of 0 at its bottom point and gradually expands. According to this proposal, the universe smoothly expands from a point of 0 size. Hartle and Hawking formulated an equation describing the entire sphere, the wave function of the universe, encompassing the entire past, present, and future simultaneously. This prompts contemplation on the seed of creation, the creative force, or any transitions from a time before. In a 2016 lecture at the Pontifical Academy, Stephen Hawking stated that asking what existed before the Big Bang is meaningless. According to the no-boundary proposal, time as we understand it does not exist. Hawking likened this to asking what lies south of the South Pole. Both questions don't make sense. Hartle and Hawking's proposal fundamentally redefines time, suggesting that each moment in the universe is like a cross-section of a sphere. While we see the universe expanding and evolving, real time involves the relationships between the universe's size in each cross-section and other properties, especially entropy or disorder. Entropy increases from the bottleneck to the feather, indicating an emerging arrow of time. However, near the bottom of the sphere, these correlations become unreliable. Time ceases to exist and is replaced by pure space. As Hartle, a professor of the University of California, Santa Barbara, explained, "We don't have birds in the early universe. Later, we do. Similarly, we don't have time in the early universe, but we have it later. Thus, time doesn't have a starting point in this no-boundary condition version of space-time." Hawking proposed a version of the universe without a beginning or end. As you approach this initial state, it transitions into what's called imaginary time. In theoretical physics, the Hartle-Hawking state, named after James Hartle and Stephen Hawking, describes the universe before the Planck era. Hartle and Hawking suggested that if we go back in time to the universe's origin, we would find that time transforms into space as we get closer to the beginning. This means the very start was only space, with no concept of time, making the idea of a beginning irrelevant. According to the Hartle-Hawking proposal, the universe doesn't have a traditional origin. It's a singular point in both space and time before the Big Bang. Therefore, the Hartle-Hawking state universe doesn't have a distinct starting point, differing from Hoyle's steady-state universe concept. Instead, it lacks an initial boundary in both time and space. The Hartle-Hawking state represents the universe's wave function, a theoretical framework to explore its origins, calculated using the Feynman path integral. Specifically, it's a hypothetical vector within the Hilbert space of quantum gravity theory that defines this wave function. This function depends on the metric tensor defined across the compact d-dimensional surface of the universe, where d represents the space-time dimensions. The precise form of the Hartle-Hawking state involves integrating over all possible d-dimensional geometries that satisfy the necessary boundary conditions. According to this theory, time becomes distinct from the three spatial dimensions as we currently understand them. Once the universe reaches the Planck age, a wave function like this can satisfy the Wheeler-DeWitt equation. Imaginary time serves as a mathematical concept in certain approaches to special relativity and quantum mechanics. It plays a crucial role in connecting quantum mechanics with statistical mechanics and is utilized in various cosmological theories. Mathematically, imaginary time represents real time transformed through a Wick rotation, where its coordinate is multiplied by the imaginary unit I. Now, contrary to its name, imaginary time isn't unreal or fictitious in the sense of challenging rationality, akin to irrational numbers. Instead, it's a concept expressed through imaginary numbers in mathematics. Some may see imaginary numbers as merely a mathematical concept divorced from reality. However, from an empirical philosophical standpoint, defining what is real is not straightforward. Our task is to develop mathematical models that accurately describe the universe we live in. Interestingly, a mathematical framework that includes imaginary time not only explains observed phenomena, but also predicts others that we have yet to measure, based on compelling reasons. So what defines reality versus imagination? Could the distinction be purely subjective? In the theory of relativity, time is multiplied by the imaginary unit I. This can be interpreted as a reflection of the intricate relationship between space and time, or it can redefine time itself as imaginary time, adjusting the equations accordingly. In cosmological physics, imaginary time plays a role in various models of the universe. By integrating imaginary time into the equations from general relativity, scientists can address singularities where the known laws of physics cease to apply. For instance, the Big Bang appears as a singularity in normal time. However, in models using imaginary time, this singularity can be resolved, allowing the Big Bang to function like any other point in four-dimensional spacetime. Before the Big Bang, there existed nothing but a vast expanse of energy and time. The ongoing scientific debate about imaginary time inevitably leads back to questioning the validity of the Big Bang theory. Since the launch of the James Webb Space Telescope in 2021, increasing scrutiny has highlighted uncertainties and gaps in this theory, which has been central to cosmology for over a century. A major point of contention revolves around the formation of light elements such as lithium and helium. According to the Big Bang theory, these elements, including deuterium, were supposed to have been produced during the explosive birth of the universe. For instance, the theory predicts the creation of approximately 400 lithium atoms for every billion hydrogen atoms. However, astronomers studying ancient stars within our galaxy have discovered inconsistencies with these predictions. They've observed that the amount of lithium present in these early formed stars does not match with what the Big Bang theory anticipates. These stars, which originated very early in our galaxy's history, contain minimal quantities of heavier elements like iron, which are generated by earlier generations of stars. This disparity challenges some of the core assumptions of the Big Bang Theory, prompting ongoing reassessment and debate among scientists. In many of these stars, the lithium abundance is only about 160 lithium atoms per billion atoms of hydrogen, which is significantly lower than what the Big Bang Theory predicts. Furthermore, recent data collected over the past few years shows that older stars actually tend to have even less lithium. A study presented by Lerner at the January 2020 meeting of the American Astronomical Society highlighted that observations of lithium and helium abundances in these aging stars deviate markedly from predictions, surpassing over a dozen standard deviations. This gap is widening rapidly. The oldest stars in particular possess less than half the expected amount of helium and less than a tenth of the predicted lithium levels according to the Big Bang nucleosynthesis theory. The observed levels of lithium have dipped below 1% of what was theoretically anticipated. This accumulating evidence strongly suggests that neither helium nor lithium was synthesized before the formation of the first stars in our galaxy. Equally significant is research indicating that the observed abundance of light elements can be explained by an alternative hypothesis. This hypothesis proposes that these elements were synthesized by stars during the early stages of galaxy evolution. Known as the galaxy origin of light elements, or goal hypothesis, it's based on theoretical expectations that the first stars to form in a galaxy would be of average mass, heavier by 4 to 12 times that of the Sun. These stars convert hydrogen into helium much faster than our Sun, in tens of hundreds of millions of years, compared to the Sun's 10 billion-year lifespan. As these stars near the end of their lives, they disperse helium through powerful stellar winds. Cosmic rays generated by these primordial stars colliding with other nuclei at high energies produce deuterium and lithium. Despite contradicting predictions related to the Big Bang, this data finds support and explanation through theories of galactic evolution that do not rely on the Big Bang. For instance, a paper published by Lerner in 1989 proposes that lithium is primarily formed by cosmic rays emitted from early stars colliding with carbon and oxygen nuclei, along with nuclear reactions occurring in stars during their giant phase. Lerner argues that similar stellar processes can also explain the observed abundance of helium and deuterium in the early universe. Recent studies, incorporating new calculations based on the goal hypothesis, further suggest that early stars not only account for the observed quantities of helium, deuterium, and lithium, but also produce other elements such as carbon, boron, and beryllium in amounts consistent with what is observed in the oldest stars. Lerner explains that the goal hypothesis was first fully published in his 1989 paper, although it had been discussed by others before then. The predictions in that paper have been confirmed by decades of subsequent observations. Unlike the predictions of the Big Bang hypothesis, the new work presented at this conference refines the predictions, making them more accurate and based on our broader current knowledge about the evolution of stars. These conclusions, derived from observing old stars in our galaxy, are supported by recent observations of conditions in newly formed galaxies. These galaxies are extremely bright, converting hydrogen into helium at rates hundreds of times faster than our current galaxy. Research published last year by other scientists showed that their brightness is controlled by stars with masses around 8 times that of the Sun, as predicted by the goal hypothesis. Structures too large to form in the time since the hypothesized Big Bang. Now, the Big Bang theory suggests that the universe began with an almost completely uniform distribution of matter. Over time, this matter formed structures, from stars to galaxies, which eventually combined into superclusters. However, larger structures have been found earlier than expected. In 2013, a team led by Roger C.L. discovered a massive collection of quasars spanning over 3 billion light-years, existing billions of years ago. This structure seems too large to have formed within the conventional cosmological framework. Even larger galaxy structures were found in 2016 by Hoff and colleagues. Lerner noted that given the current low velocities of galaxies, the large-scale structures we observe would require hundreds of billions of years to form. In 1986, Lerner used plasma physics to predict the fractal structure of the universe, including structures with diameters of up to billions of light-years, which were discovered later. Now, according to Lerner's theory, these structures could only have formed in a universe with a history extending back more than 14 billion years. Another point of contention among scientists is dark matter. The Big Bang theory suggests that most of the universe's matter is dark matter, unlike any matter found on Earth. However, increasingly sensitive experiments on Earth have failed to provide conclusive evidence for these dark matter particles. Additionally, astronomical evidence has also called dark matter into question. One simple piece of evidence is the relatively low speeds of galaxies in the universe. The large amount of dark matter predicted by the Big Bang would create gravitational forces causing galaxies to rotate at speeds of hundreds of kilometers per second. However, the observed average speed is only 50 kilometers per second, which contradicts the need for such a large amount of dark matter. Researchers Barev, Selos, Labini, Monori, Pono, and Terra have shown that the fine distribution of dark matter required to avoid these high speeds does not match the clumpiness and homogeneity observed in matter at all scales. Additionally, the satellite galaxies of both the Milky Way and the nearby Andromeda Galaxy have disc-shaped configurations, which is what we'd expect if gravity comes from ordinary matter. If dark matter were responsible for gravity, these satellites would be arranged in a random sphere. This evidence, supported by Pavel, Kupa, and many other researchers, challenges the dark matter hypothesis. Alm and Kupa in 2018 highlighted that the unavoidable effect of viscosity in dark matter would lead to galaxy groups merging so rapidly that very few would be observable, which contradicts the existence of many such groups. There are simpler alternatives to the Big Bang theory for explaining the data. Over 30 years ago, Parrott and Green showed that electric forces could account for the constant rotation speeds in spiral galaxies, often cited as key evidence for dark matter. These speeds reflect the velocity of anisotropic plasma in a galaxy, influenced more by electrical forces than gravitational ones. Researchers like Gasha and Braytek have found that in the outer regions of galaxies, including the Milky Way, gas moves faster than stars, a difference explained by the effect of magnetic fields on the gas. More recently, Connell and Kov provided convincing evidence of the magnetic field's impact on the motion of stars. They found that many nearby stars are embedded in filaments that last for hundreds of millions of years. Although the authors didn't specifically conclude this in their paper, it's evident that gravity alone can't create such long-lasting structures. However, magnetic fields with observed intensities can influence the dynamics of dense gas filaments, which can then control the gravitational motion of stars within them. This suggests that magnetic fields, rather than the presumed dark matter, might provide additional observable forces in galaxies. The idea that the expanding universe is the main foundation of the Big Bang theory has encountered challenges. Observations of the sizes and brightness of thousands of galaxies contradict predictions based on this hypothesis, leading to a significant reevaluation. A paper by lead scientist Eric Lerner, published in the monthly notices of the Royal Astronomical Society, titled Observation Inconsistent with the Predictions of Galaxy Size and Surface Brightness Growth Based on the Expanding Universe Hypothesis, revealed that predictions about the growth of galaxy sizes do not match actual data. Proposed mechanisms for galaxy development, like galaxy mergers, also conflict with observations. The paper notes that the data aligns better with the idea that the universe is not expanding and that the redshift of light is caused by an unknown process. This research tests a prediction from the 1930s regarding the Big Bang hypothesis, suggesting that objects at great distances should appear larger rather than smaller. This prediction, reiterated through the 1980s, was not confirmed by the Hubble Space Telescope in the 1990s. Instead, Hubble's images revealed that the farthest galaxies appeared smaller than expected. A group of researchers proposed that galaxies actually grow in size over time. This means that very distant galaxies, observed as they were billions of years ago, were much smaller than galaxies today. Thus, the intrinsic size of galaxies, as understood in the 1990s, contradicted the optical illusion predictions from the 1930s. In Lerner's paper, predictions from developing galaxy theories were tested using the observed sizes of thousands of spiral and elliptical galaxies from Hubble Space Telescope observations between 2004 and 2014. The paper limited the samples to galaxies with similar near-ultraviolet brightness. The observed data did not match predictions that galaxy sizes increase in proportion to the rate of the universe's expansion. Additionally, Lerner highlighted that the merging process for the development of elliptical galaxies occurs at a rate nearly 10 times slower than the growth rate suggested by the hypothesis. A more significant inconsistency is found when comparing the gravitational mass of distant galaxies, determined from their rotation speed and size, with the mass of their stars, calculated from their emitted light. Predictions based on the expanding universe theory result in a gravitational mass smaller than the mass of the stars, which is impossible. While predictions about the expanding universe don't match the data, Lerner points out that predictions based on a non-expanding universe accurately describe both spiral and elliptical galaxies at all distances, with only a few % deviation. In a non-expanding universe, galaxies of a certain brightness have the same size regardless of their distance, just as the hypothesis predicts. Lerner suggests that in this model, the simple linear relationship between the redshift of light and distance is due to something affecting the light as it travels, rather than the expansion of space. Although the exact cause is unknown, the linear relationship and the non-expanding universe make accurate predictions, unlike the expanding universe model. The Big Bang theory faces several challenges that proponents tend to dismiss as anomalies. These challenges directly contradict the theory's initial predictions. To reconcile these discrepancies, supporters continuously introduce new parameters to accommodate data that doesn't align with the theory. This approach has led to the adjustment of over 20 parameters, preventing the theory from making accurate predictions, a fundamental aspect of robust scientific theories. Conversely, hypotheses proposing a universe without a beginning in time and without a Big Bang offer a simpler explanation for the data that contradicts the Big Bang theory. So this concludes today's video. If you enjoyed watching it, please give it a thumbs up and stay tuned for more videos like this.